So far, regarding the material that I shared with you, is there any question?
Oh yeah, actually I have one little question about BCD, if we can do an example.
Sure.
Okay, so I just pulled these two random numbers out of my head. So when I was trying to find the BCD, so it was like 426 BCD plus 572 BCD.
1 second. So you want what? 400 what?
426
426.
plus 572.
Okay. And then we're gonna add them, right? Okay. So if we add them, you're gonna have here 6, 2, 4, 2, 7, 5. Pretty much, you're gonna make it like binary normally, but so it's gonna be here 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, right? 0, 1, 0, 0, 1, 2, 3, 0, 1, 0, 1, 0. Okay, adding them, so going to be here 0, 1 plus 1, 0, and you have the 1 here. So going to be here 0, and you already have here 1. Sounds good? Now we're going to move to the second part. So going to be here 1, 0, and they're going to be here 1, so going to be 0, and they're going to be here 1. There are going to be 1, 0, 0, and 1. Okay? Sounds good? Now, let's see. This is what? 8. Do you agree? So it doesn't need anything to go back into the ring. It's between 0 to 9. So you already have here 8. This is what? 9, right? So it's also into the ring. This is what? 9, into the ring.
Okay, I see what I did wrong. I accidentally carried the 1 over a couple of times on accident when I was doing the math.
No issues. I think one of you asked me last time about, the gray code. Is there a way to return it back to the BCD? I think it was Leslie or something like that, right? One of you asked this question. So I'm going to do the gray code again, and then, I will share with you what is gray code. We stopped last time on a gray code. Do you remember? So gray code. What is gray code? So, all of those guys are from the family of the binary representation coding. So we use binary, but then, we are into 0 to 9, between 0 to 9, okay? Because, the decimal, it's 0 to 9. Sounds good? Gray came and say, I would like the neighbors and numbers to have less number of variants or switching, and he actually liked it to make it 1. So we know that, in numbers in the BCD or all of these binary coded systems, it's 4 digit in a binary, right? 1, 2, 3, 4. And those 4 digit in a number, it will be what? From 0, 0, 0, 0 up to 9. Correct? And we mentioned that, from 10 up to 15 is undefined for us. Correct? Now, if you look to the number here, for instance, Gray said that, those guys are still in the binary, right? So let's label it as, B0, B1, B2, B3, right? And why I make it 0 and 1 and 2, 3? Because, this is 2 power 0, 2 power 1, 2 power 2, 2 power 3. Okay? He like to move to the equivalent, was it going to be what? G3, G2, G1, G0, right? Now let's get some number and see whether that, this guy is talking correct or not. We said, the neighbors maximum switching, it should be what? 1. So let's pick a number. What number from 0 to 9 we can pick? Let's go into 3, for instance. 3 is like 1, 1, 0, 0, right? Let's go in 4. 4 is 0, 0, 1, 0. So that mathematician came and say, I would like every single number and the neighbor will be what minimum switching, which is 1. This is the minimum thing that you can have, right? In the BCD, for instance, if you look to this one, right, you will find 1 turn it to 0. So this is 1 attempt, right? One thing. Then that's 1 went to 0 again. So that means 2 is switching. Then 0 to 1, that's a third switching, right? And then 0 to 0 is still the same. So that means when I'm moving from 3 to 4, that I use what? 3 switching. So what happened? I actually expend more power. I spend more power. And if I keep pushing streaming data from the source to the drain or the transmitter to the receiver, and there's something wrong can happen in the middle, we can have data corruption or data corrupted data, I'm sorry. If the data corrupted, that means, let's say that, I'm in here in my base station, and then, the satellite in the top, and then, I send an order to the satellite to go to this way, a little bit far from the gravity, right? But then, something wrong happened, like a lighting happened, then, because it's electromagnetic wave, so, the message say that, no, go to the lighting. Then, the satellite will just go like breaking in half. Does that make sense? So he trying to make it the best of making it small. So what he said, I'm gonna give you an equation. What is this equation? This is the most significant bit, and this is the least significant bit. Here is the least significant bit, and this is the most significant bit, right? So he said, G3 is equal B3. G2 is equal what? B3, and added to B2 without what? Without carry, right? Later on, you guys will hear this is called XORing. So later on, that will be something called XORing, which we're gonna hear about it like maybe in 25 minutes. Okay, so basically, it's gonna be B3 XORing B2. That's called XORing. That means I'm adding without carrying. Okay, now G1 is what? It's gonna be B2 with B1, and G0 is gonna be what? B1 with B0. Okay, now let's apply this into the 3 and 4 and see what will be the output, right? So go into the 3. If I go 3, that means my G3 is equal what? 0. I'm taking it as it is, right? For the G2, it's gonna be what? It's gonna be the neighbor. So this one and this one will be added to each other, right? So gonna be what? 0. Then G1, this one and this one will be added to each other. So what the output will be? It will be 1. And then those neighbors will be added to each other. So gonna be what? 0. So 3 in the gray code is 2. Right? Now let's have 4. 4, this is 0. And then 0 plus 1 is what? 1. And then 1 plus 0, 1. Then 0 plus 0, 0. So 4 in the gray in the binary on the BCD is equivalent to what? 6, right? Now let's see whether this guy actually realized what he was seeking or not, right? 0 turned to be 0, right? 1 is 1, no change yet, right? 0 went to 1, first change, right? Then 0 went to 0. So that means he succeeded in the way that he presented 3 and 4 as neighbors with what? Minimum number of changes or switching. They call it switching. So every switch, it will cause you what? To spend more power. Then one of you asked me last time, is there a way for me to return it back to the binary form? Yeah, if you do the same process again, it's a symmetrical. So for instance, if you say 0, 0, 1, 0, right? Do it again, right? You take 0. Then 0 with 0 gonna be 0, right? 0 with 1 is gonna be 1, 1 with 0 gonna be 1. That was a 3 before, right? So I return it back or not. So it's a kind of like a process. It can push you from the gray back to the BCD binary BCD to the gray. That makes sense? Okay. Any question regarding this part?
So when you're adding, you go from left to right from G3 to G0. That's what you're going for.
Most significant, less significant. Remember
Okay.
this, okay? Most significant, go as it is. Then you start the neighbor here, add, get this one. Add those two guys, they get this one. Add these two guys, get this one. If you don't like this representation, this is a representation, right? G3 is B3. G2 is B3 plus B2. G1 is what? B2 plus B1. G0 is basically B1 plus B0.
Professor?
Okay? Yes.
So what exactly is the pattern? Is it like if I have 4 in binary and I use the gray thing, I'm going to go to 3 and so forth? Like if I have 3 in binary and I use it, I'm going to go to 2?
Yes. It's not about the pattern. The whole idea that he likes when he will send data to have less number of what? The idea was based on the power. It wasn't even based on any numbers. It was based on, he liked to transmit data with low power, especially when they started transmitting, receiving data through the Atlantic Ocean between United States and Europe. That was the whole idea, because normal binary, as you have seen, right, 3 and 4 is really costly because 3 switching happening. So chances for error will happen, it's going to be really higher. You understand my point?
Yes.
Okay. Now we're gonna move to the last part of the chapter. We are really slow, but we have to speed up, by the way. Anyway, which is called priority bit, or the or you can consider it like fixing bit, or like a detector, a kind of detection. It do some detection. What is this? Okay, here if you have a 7-bit representation of a number, so B0 to B6, right? B0 to B6, that means 7 bits, right? 7 bits. Which is pretty much like Ascii code. What is Ascii code? Every single character on your keyboard is represented in what? In a binary system, like bunch of 1 and 0s. If you make lowercase, it has a certain pattern. If you make it uppercase, it has a certain pattern. And they call this ASCII, ASCII. It's American Standard Coding something. Okay, so you will find it in all different type of what? Keyboards. That's why, the keyboard layout is different from country to the others. So for instance, British keyboard layout is completely different than, American keyboard layout. They have their own table, you know what I mean? For instance, Norwegian, I lived in Norway, so, we speak Norwegians, right? So basically, we have a different layout, right? So for instance, you guys have been playing with Raspberry Pi before? Have you ever touched Raspberry Pi? In the Raspberry Pi, there is something in the coding that tell you go and change the layout of the keyboard, right? Sometimes, you will just push the character, you will find yourself doing something else because, Raspberry Pi is actually built by an ARM company, and the ARM company is a British company. So they have a default of the British standard, something like that. Later on, I don't know how many of you heard about Raspberry Pi. Have you, how many of you heard about it? How many of you even tried to use it?
I've used a Raspberry Pi before. I've
Yeah,
got 2
so
of them.
have you seen this part, right, of the changing the layout of the keyboard, right?
When you do Raspberry config or Raspi config, it asks
Yes,
you to do that.
yes, in the pseudocode, yes.
Yep, in the pseudocode.
Exactly. Linux. I love Linux. They call it Raspberry, but in reality, it's a version of the Ubuntu. Okay, anyway, now imagine the following. Imagine that I'm sending this character to a certain place, right? I'm sending it to let's say that to New York. I'm sending message from California to New York, and this message have bunch of characters, right? So how New York will figure out that these characters are not corrupted, right? So we're gonna use something is called odd parity, or even parity. This is actually, it was a different topic. I'm sorry. It's called parity bit. So odd parity or even parity bit. What is this? Let's say an odd. An odd, that means I have to add an extra bit, which is bit number 8, and it's gonna make the whole entire thing look like what? Odd number. Example. So let's make it on what? Let's make it on 4-bit, right? Or let's make it in 3-bit. Something easy. So B0, B1, B2, and this is the parity and it's odd. So, if the number is like 1, 1, 0, like this, right? This has to be odd, right? So what I'm telling you consider it is like a word, and this bit number 4, it will make all numbers of 1 in this segment odd. So now we know 1 and 1 and 0. How many 1 we have? We have 2 1s, right? This is even, not odd, right? So this one, it has to be 1 to make this segment of 4 odd. Okay? Let's do another example. Imagine the phone. It's like, 0, 1, 0. And I need to know what is this gonna be. So I have here 0, 1, 0. I just have 1. 1 in this case is what? Odd, right? So I don't need to add anything else, right? So this, in this case, it's gonna be 0. So I'm gonna send this segments, which is the 4 digits, by this way. They're gonna check in the receiver that part, whether that is still 0 or not. If it's not 0 in that case, then something wrong happened, and then it will ask you to what? Retransmit. It's not gonna fix it, but it's gonna what? Say there is corrupted data happen, retransmit. In the P with the parity even, imagine the following. We have B0, B1, B2. Let's say also 3 digits, right? So gonna be here like, 1, 0, 0, right? This is what? How many ones we have here? We have just 1. That means it's odd, right? But I'm looking for even. So I have to put here 1. So this 4 digit will have 2 1s. Another example. If I have B2, B1, B0, 0, 1, 1, and then P even like this, right? Now, how many ones I have in those 3? I have 2. So this is what? This is even. So in that case, I don't need this to be 1. So that means, I'm gonna send it like that. So basically my P even, it will equal what? 0.
Professor, quick question. So if the bits are all zeros for P even, would it be the 0 again? Is 0 even?
Yes, it should be. Yes.
Okay. Got it. Thank you.
You're welcome. Any other questions? So if there is no questions, I would say that, we finished chapter 1. So we learn what is the number systems. We learn how to move from a number system to the others. We learn what is binary coded systems. And we took example of the binary coded system as a BCD, and we learn how we actually work with the BCD. And then as another example of the the binary coded system, we learn something called accessory, which is basically incrementing the BCD by 3. And then, the other one as an example for other system for the binary is called gray code. And in a way that he's trying to decrease the chances of any corrupted data to happen while you're transmitting and receiving data. And then, we came into something to check whether that, the data have been manipulated or corrupted, which is called parity bit. And, we describe it. And in the top of that, I give you a hint about something is called Ascii code, which is basically a bunch of 1 and 0s. You can find the table in Google. Just write Ascii code of the American keyboard layout or something. It will give you the whole entire thing. If you like, for instance, write A uppercase, what it will be the representation in a binary and hexa, and so on. And I can say that, now we are ready to move to the next phase of the digital logic design, which is basically learning more about what logics and also Boolean algebra. Okay, so now we're gonna learn two things, which is something called gates.
Is there a quick question?
Yes.
The P even only exists in 4 digits?
Which one? Yeah, P will make it 4 digits.
So we can't have like more, or just 4 is
It has to be just 1 bit, right? So if you are sending 3-bit, number 4 will be the P, right? If you are sending 5 bits, the parity would be number what?
6, right?
Exactly.
Okay, for sure. Thank you.
And then the
We're gonna choose
parity
the
should
value,
be
right?
odd or even. Which way are you gonna use?
Okay, thank you.
Make sense?
Yeah.
Okay, so we're gonna learn something called gates and what is those gates actually doing, and then also we're gonna start working what Boolean algebra, which is the relation between inputs and outputs in a logic form, not in mathematics form. Okay. So gates, they call it binary gate. How it gonna work? Some people start with Boolean algebra, and from there you're gonna move to the binary gates. Some other people started from the binary gates and then return it back to the Boolean algebra, and then connect between of them. Then you will move forward. Which philosophy I really like? I like to give you a hint about what is binary gates. You start think about it while I'm telling you what is Boolean algebra. Then it will be more easy for you to understand. Okay, so binary gates. We have 3 different type of gates. We call them basic or essential gates. Describing the relation between the input of these gates and the output, we do it through something that's called truth table. And everything here is binary. So we have 3 essential gates, and from the essential gates, we can build some other gates. So what of those are essential gates? So the essential gates is basically number 1 is called AND gate. Number 2 is called OR gate. Number 3 is called NOT gate or inverter. So we have AND, OR, NOT gate. So how I'm gonna represent the information out of the gates? I'm gonna use 3 different forms. What is this? 1, the symbol of the gate, the official symbol. Second, it's gonna be the truth table. The third will be what? The Boolean equation. So we have 3 things we're gonna use for every single gate: the symbol, the truth table, and what? The Boolean equation, which is the equation describing the relation between input and output. Okay, let's start with first one. The first one is called AND gate. So AND gate, how does it look like? Here is my AND gate. What of those are the inputs? And this is the output. So AND gates can have multiple inputs. It can have infinity number of inputs. The minimum number of inputs we can have 2. Okay, so minimum number of inputs 2. So in that case, I can redraw this to be look like that. This is the P output, and this is the input. X, Y. Of course, you have 3. That's called 2 input AND. Okay? You can have 3, which is like this. Sounds good? So this is called 2 bits input AND gates. This is 3 input AND gates. You can have n input AND gates. So now we satisfied the first part, which is making the symbol for the gate, right? We're gonna use it for implementation. So remember how it looked like, please. Okay, now the second part, which is the relation between the input and output. So I'm gonna build the Boolean equation for the AND gate. So P is the output, right? P is the output. So I can say P is equal. P is a function of the input ports, right? So P, it's a function of X and Y. So I can write here F as a function of X and Y. That means, X and Y, when they are changing, P will be changed. That makes sense? And what is the relation between the input and output in this case? Is equal to what? X, Y. What is this actually doing? This is not the normal multiplication we have in what's called in the math. It's called, you multiply them, but it's not completely multiply them. It's called existence of the inputs. So what does this mean actually? It means the following. If X and Y are exist, P will be exist. Again, it means X exists, that means X is equal high. So let me tell you this. High for us is actually equal 1. Low for us is equal 0. That makes sense? High, that means I have volt, right? It's connected to the source, VCC. Low, that means I'm connected to the ground. So that means I'm connected to the ground. And here I'm connected to the VCC, which is a source. Okay? So what is say? If X and Y exist, P will exist. What does it mean? If X is equal 1 and Y is equal 1, then P will be 1. Other than that, it will not be what? Exist. That means it will be 0. So what is the best way to actually represent it? It's like X multiply Y, right? That makes sense? Any questions so far regarding this part? Hello? No question?
No, sir.
Thank you, sir.
So now, based on this information, we're gonna make a table. They call this table what? Truth table. Truth table. What is truth table? It's a table describing the relation between inputs and outputs. Okay? How many inputs we have here in this example? Huh?
2.
We have 2, right? And this 2, I can just write here X and Y, right? So based on the number of inputs, I can draw the relation to the output. What does it mean? If this X and this is Y, how many we have? 2, as you said, right? So that means, and this X and Y represented in what? Binary. Do you agree? So I can say 2 power number of inputs. It will give me how many states this table will what cover?
4.
That makes sense? So that means 2 and here 2. So that means we have 4 states What those states? That mean here 1 state, 2 state, 3 states, 4 states, right? And we said x and y what? Binary, right? So it's basically here 0, 1, 0, 1, here 0, 0, 1, 1. Why? Because do you remember 2 power 0, 2 power 1 story, right? 2 power 0, here 0, that means, you know, 1, 1, 1 neighbors. 2 power 1, that means, you know, this 2, and then, you know, it will jump to be 2 and so on. So did you see what I'm doing? There is a possibility x is equal 0 and y is equal 0. There is other possibility x is equal 0 and y is equal 1. There is other possibility x is equal 1 and y is equal 0. There is another possibility that x is equal 1 and y is equal 1. That makes sense? So those are the states this table is covering. You guys agree? So now how I'm gonna fill the output? The output will be filled based on what? The facts equation that I already mentioned to you, right? So x times y, which is mean if x and y exist, the output will exist. If not, nothing will be coming out, right? So how can I translate this? If x and y exist, the output exists. Anything else, there is no output. Any questions so far?
Sorry, if it was, so is it always the bases too?
What do you think?
What the base is, so there's
Why the base, from your point of view, why the base is 2? Why this
because
is
it's
2?
because it's a binary, right?
Yes, sir.
Awesome.
Okay.
The base is how many inputs we have, isn't it?
No, the exponent is the number of inputs.
2 power number of inputs.
Oh,
Awesome. Thank you, sir.
You are welcome. Let's do it in 3. Let's make this 3. What do you think? Let's see, right? So let's make 3 here. Look. X, Y, Z, and P, right? How many inputs I have?
3.
3. So that means how many states I should have?
8 then.
8.
Nice.
In that case, I
Makes
would
sense.
say 1,
Makes sense. I think I'm
2,
getting this.
3, 4, 5, 6, 7, 8. Right? Let's fill it. So here 0, 1, 0, 1, 0, 1, 0, 1, because this is 2 power 0. Now it's 2 power 1. So that means it's going to be what? 0, 0, 1, 1, 0, 0, 1, 1. This is 2 power what? 2. That means 4 of them 0. 1, 2, 3, 4. 1, 2, 3, 4. So I filled all the possibilities I have, right? Now, equation, it will be what? P as a function of x and y and z is equivalent to x times yz. That means if all of them exist, the output will be 1. If not, it will be what? 0. Make sense? Simple wise, it will be like this. Right? So far, so good.
Yep.
Super. Now, if so far, so good, let's play a little bit. How can I build 3 inputs AND gate using 2 inputs AND gates?
Sorry, can you repeat that again?
If somebody telling you that, you know, I need to build a circuit, you know, here's the box. And this box, it has X and Y and Z and the output P. And I'm telling you, the only Lego set I have in my hand, 2 input AND gates. I just have 2 input AND gates. I don't have this 3 input AND gates anymore. So the best way to do it, I will say, okay, here is my first AND gate. I can connect it to where? But this is not enough. So I can take another what? AND gate. And I connect it to what? So using 2 inputs AND gates, I already give you what? The same effect of what? 3 input AND gates. Let's see whether this thing is gonna work correct or not. Right? If it's actually reality or not. So X and Y is ANDed together. Do you agree with me? Let's call this thing W. Okay, so that means W as a function of X and Y is equivalent to X ANDed with Y. No more multiplication. We don't say multiplication. If we see this, that means we are doing what? AND, right? Then the P as a function of W and Z is equivalent to what? W ANDed with what? Z. Right? Do you agree?
Yes.
If we take W and we put it in the P, so pretty much we are saying, P is equivalent to Z, and we take W to be X, Y equivalent to F, X, Y, Z. What I'm doing now is a kind of what? Boolean algebra. Does that make sense?
Yep.
Okay. So for now, just for now, later on, I'm gonna bombard you with a lot of examples, chapter 2. But at least now you understand what is AND gate. That makes sense? We know that what is the symbol of the AND gate. AND gate's kind of similar to multiplication in our life, which is basically, if both are 1, the output will be 1. Other than that, everything will be 0. Make sense? And we also learned something called truth table. Now we're gonna do the same game with what? OR gate. OR gate. So we're gonna make like this and say number 2 OR gate. So first we're gonna look to what? The general definition of OR in terms of what? Drawing the symbol of it, right? So the symbol of it is look like that. So stick with the notation we are using here. That's called notation, following the notation I'm doing. So this is my OR. Also can have N inputs and 1 output. The smallest I can have is what? 2 inputs. So that's actually my smallest. X, Y, and call this P. Okay? Now we need to move to what? The Boolean equation representing the relation between the input and output. Okay? OR means if one of them exists, there is an output. It's called OR, right? Like, if X or Y, that's why it's called OR, right? If X or Y, P's exist, right? So let's put it in an equation. So P is a function of X and Y together as a variable is equal if X or Y exist, P will come out. What does that mean? If X exists, okay, P is correct. If OR is there, Y is there, it's correct. If both of them are there, it's also correct, right? That's called a logical operation. So now this actually can represent it like you are adding, but you're not adding. That's not normal adding. It's like the existence of the thing, okay? So the table out of it is gonna be what? We build what is called truth table of OR gate, right? So I have here X, I have Y, and I have what? P. How many inputs this table will cover? Same thing. How many it will be?
4.
So 1, 2, 3, 4. 0, 1, 0, 1, 0, 0, 1, 1. Yes, it's like taking the composite of the two functions. Yes, yes. We're going to talk about this more. But anyway, let's actually apply this in the P, right? This is exists perfect. This is exist perfect. Both of them exist all perfect. There is no here. So that's basically I already filled the relation between what? The input and output.
So 1, 1 is not a 0. It's 1, 1 is a 1.
1, 1, it will be 1. It's not adding
Okay,
anymore.
got it.
Because
Oh,
it's
got it.
existence. Okay?
Oh, okay, okay.
Okay, so this is my P. What about if I have 3? If I have 4? If I have n, what will happen? Same thing, right? So let's apply it on 3. So 3 input or gate.
So it'll be everything except for the one with all zeros will be a 1.
Let's see. So anyway, I'm gonna be here 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, and here's what P. Any existence 1, right? Here 1, here 1, here 1, here 1, here 1, 1, 1, 0. And same thing about distributing in the algebra we're gonna do there, right? So it's basically like if I would like to build it with 2 OR gates, I'm gonna do it exactly as I did with what? With n. So gonna be here 1, x, y, and then another one, you're gonna take z, and they're gonna be p, and those two together will make it for me what's happening as I'm looking for. And the chapter 2, or more into when we'll go deep, we're gonna talk about timing. But at least for now, we see that we can connect the stuff without including time. When I say timing, what does it mean? We are engineers, right? So that means everything we process, it takes time to process. You agree? So if I make a box like this and I put some inputs to here and I get an output here, this output will not come in t is equal 0, right? You agree? And this output will take what? The response time of this box, right? So that means also OR has response time and it has response time, and that will be affecting in how much time the process will happen. Okay, but at least is it OR gate clear to everybody? Is it AND gate clear to everybody? The way that I'm actually doing it, and you have the symbol, you already have the equation, and also you have the table. Is it clear? We also learn what this truth table means. We also learn how to calculate number of states based on number of inputs we have. Clear, right? Okay. Now we're gonna move to our lovely third player in the family of the gates, and it's called NOT gate, which is really easy. NOT gate, if you see something, you invert it. So it's called NOT gate. NOT gate. What is actually NOT gate doing? So let's do it. So NOT gate, in terms of the symbol wise, it's like a kind of this symbol and inversion here. Normally in the circuit, when you guys go in a higher level, you will find this buffer. What does it mean? That means if you have I and O, that means O is equal I. But if I put this circle, that means if I put here I, that will be the I negation. What is this? If you remember from the complement, do you remember the complement? Do you remember when I said, if you have 1, it will be 0. If you have 0, it will be 1. This is basically how it's actually written. So pretty much I can say if this X and this is P, let's stick with our variable names. So I don't have many inputs to the inverter. I just have one input, right? So in that case, I can say P as a function of X is equivalent X complement. And if I like to make a table describing the relation, so how many inputs I have? I just have X and I have one output. So if it's X, so gonna be 2 power 1, so gonna be 2 states 0 and 1. If the input 0, that means it's gonna be 1. If the input 1, it's gonna be what? 0. So far, so good. Those are the basic, those are the fundamental gates we're gonna use, and we're gonna stick with them for the rest of our what? Course. We have AND, we have OR, we have what? Not gate. So the term, when I see X time Y, that's no longer called multiplication. That's called what? X ANDed with Y. When I see X with, you know, the addition sign with Y, that means is no longer adding. It's called what? And sorry, ORing together. Okay, doke. If there is no questions, I can move forward. If there is a questions, I can stay more. Which way you guys prefer?
For the NOT gate, why is X 2 to the power of 1 and not 2 to the power of 0?
Because number of inputs, what? 1.
Oh, okay.
Right? Do you remember the equation? 2 power number of inputs equal the states. And exactly, if X is equal 0 and 1, 1 state, 2 states, equal 2 states, right?
Yeah.
Any question? There is no questions? That means, you know, we are in a good shape.
I think so. Or
I
we
mean-
just don't know what questions to ask.
Nope.
I mean, like, are there
no
examples like for this that we can write down, or
Huh?
are there examples that relate to these sort of thing?
Yeah, don't worry. Everything will be easy. Let me just
Everything's
let me-
easy.
let me
Like it.
complicate stuff. Okay, now I know this is what AND operator. This is what this is OR operator. This is what the NOT operator, right? That's called operators. Do you agree? I mean, so if somebody telling you X, Y, and Z, this is an operation happening here. What I'm doing here, I'm actually what? I'm ANDing X with Y and Z. Do you agree? So I can say this is equal to X, right? So I'm distributing and you're doing what? It doesn't matter where is the order of the variable, still they're gonna be ANDed together. This is exactly the same relation. Do you remember when we learned, you know, multiplication and adding? You know, we was doing all of this distribution thing. They call those guys postulates. Okay, they just call it like that, postulate. Like, you know, if I say X, Y with Z, this is gonna be X, Z, Y, same thing, right? So it doesn't matter, right? Let me make it even more fun. So let's say that, you know, I have F as a function of X and Y and Z equivalent to X time Y ORed with Z, right? So you can actually distribute X, right? So you can come and say X with Y ORed with X and it with Z. So this thing is equivalent to that thing. So did you see, you know, just for fully understanding this symbol and an OR and NOT gate, make it easy for you to understand that, you know, you can make it in a bigger number of variables with a different relation. That makes sense? Let's actually add all of them together in one equation. Let's imagine that it's actually X complement, Y, Z complement. Would it affect if you distribute? Of course not. You can distribute still, right? So you distribute, going to be X complement, you know, ANDed with Y, and then that will be ORed with what? X complement, and it was a Z complement. In this equation, if you flip everything, how gonna be? That's gonna be a NOT gate. And then that's gonna be OR gate, and then that's gonna be NOT gate, and then they're gonna be OR together. Sorry, and together, and then that everything will be OR together. You understand what I'm saying? So now we understand why I need you to fully understand what I did with AND and OR and NOT gate.
Sorry, Professor, can you draw the schematic for that one?
Basically, you're asking for implementation. See, the schematic, that's a very good question, which is make it easy for me to push forward. So when you are moving from the equation to the drawing, that's called implementation. To be very precise, it's called gate level implementation. Gate level implementation. So your question, can you make the gate level implementation equivalency of this Boolean algebra or this Boolean equation, to be more precise? Very good question. So
sorry, one question. So would the input be still X, Y, and Z?
Yes.
Right? Okay.
Yes. Which is basically your wires. When you go in the 2300 lab, right? You connect wires, right? So if
so the input's not okay. All right. Go ahead. Sorry.
No, go ahead, please.
Oh, I was gonna say, so the inputs are not like X naught and Y and Z naught. That's not the inputs,
I will
right?
show you. Your input is X, Y, and Z.
Oh, okay.
This is a raw, right? So basically, here is my X, here is my Y, and here is my Z. Those are wires connected maybe to the ground or connected to the VCC, right? Now, let's make this implementation happening. So we notice that X will be complemented sometimes, right? So what I can do, I can just do it like this. This is my X complement. And also I notice Z is complemented. So it's gonna be like that. Right? So far I finished what? The complementation of the X and Z, but I don't have any complementation to Y in the whole entire equation. Do you agree? Now the time is actually to do the relation between of the complement of X and Y. So you can just go ahead and do like this. And maybe I can use a different color to make it easy.
It's the Y. Professor, you're going to Y and Z not.
Oh, I made a mistake. Okay, I'm sorry. Maybe I can use a different color. I'm sorry. So what is a different color I can use? I don't like this guy. Yes. Did you see this little dot? It's connected, Then, is it done? No. To get the P, which is the output, you have to OR, right? So you go like this.
Makes sense.
So what I build in front of you is like I have a circuit here, and I put the X and Y and Z as an input to it, and I get the P output like this.
Why would there be an OR gate between X and Y and an AND gate?
Okay, let me show you. This is X complement, right?
Yeah.
And then X ended with Y, right?
Yeah.
X complement ended with Y, right? Then consider this is called W. So this is W, right? Then X complement ended with the Z complement. So X complement ended with Z complement. Let's call this, for instance, N, right?
So I got it. I confused myself. I got them confused.
So you're fine, right?
Yeah, I'm fine. I thought those were OR gates and those are right. Sorry, that was my bad.
Oh, you're fine. Okay, so I can just call this and, or, and, not. Anyway, so what we did now, we built a circuit, which is called gate level implementation of the Boolean algebra or the Boolean equation, to be very clear, right? What about if I want to see the truth table of this?
Very tricky.
That's not really tricky, it's really come on, it's a piece of cake. So anyway, here's X. You know what? Nothing is really hard in this life, you know.
Oh, there's gonna be still 8 inputs, I guess.
Exactly.
8 total. We got it.
1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4, right? And now I'm looking for what? My P. It's a little bit tricky, right? Because, you know, I'm going to take it one by one in the equation, right? So try it in the equation. Or you know what? Why we need to try in the equation? We can try it even in the gate level implementation, right? If X is equal 0, so going to be here 1, right? Then, you know, Y is equal 0. So 1 and 0 ended together. Do you remember from the table it will be what? It's n multiplication, right? So we're going to be 1 and 0. So there's going to be
0.
Then, you know, that's actually 1. And, you know, this is 0. Going here to be 0 or to be 1. So 1 and ended was going to be 1. Then, you know, 0 or 1. So that means they're going to be 1. So using this little itty bitty information about or and not help me to build a bigger circuit and even build the table describing the input and output between of them. Right? Let's pick another number. So let's go into this state, for instance. You know, let's have a different color. So if it's still 0, so I know for sure this branch is going to stick 1 and this stick 1, right? Now I'm going into Y is equal what? 0 still. So this branch will ever stay 0, right? But, you know, this branch, when Z is equal 1, that will be flipped to be 0. So then, you know, that will come out to be 1 ended with 0. It's going to be 0. Those two guys are 0. So in this case, it's going to be 0. Right? Then you move more fast. So in X is still 0. So in all cases, since X is equal 0, it's causing the whole entire branch is actually changing the behavior, right? So look, here is X is equal 0. So it's equal 1. So I have here 1 here and I have 1 there. And then, you know, I have my 1 in the Y. So I have here 1. So that's actually flipping. So 1 ended with 1. So it's equal 1 here. And then, you know, I go in the Z is equal what? Z is equal 1. So they're going to be 0. So I'm pretty much know, since, you know, one of the branches is equal 1, that is taken as 1. Right? And you can continue the rest by yourself. And if you have any problem next time, you can just let me know and I can repeat it. Just practice this, please, by yourself. Okay? So, is it everything now is clear, kind of?
Yeah, it's fun.
Perfect. Now I'm gonna give you a little bit fun stuff, you know. If somebody tell you X ORed with 0, what the output will be? Huh?
It'll be whatever X is, right?
Correct. You know, it should be X. Let's see whether that, you know, how we can prove it, right? So assume X is equal 0. So in that case, it's going to be 0 ORed with 0 is equal 0. Assume X is equal 1. So going to be, why is this one different? Okay, 0. So we're going to be what? 1. So when X is equal 0, the operational is going to be 0. 1 is equal 1 is equal 1. So that means it's actually X ORed with 0, it should be X. Right? Let's have more example, which is basically X ended with 1. What this combination thing will give me. So let's, I'm not going to put the conclusion. Let's actually make it like in a systematic way. So assume X is equal 0. So I know that for sure 0 ended with 1, it will be what? 0. Because I treat and kind of like I'm multiplying, right? So going to be here what? 0. And I'm assuming X is equal 1. So that means, 1 ended with 1 is equal 1. So pretty much, X output 1, 0, 1, 1. So that's actually also equal X. That makes sense? Any questions? Now, yes.
Oh, no, got it.
Okay. Now let's play a little bit with inversion, right? So what about if X ended with X complement? What would happen?
You have 0?
I don't know. Let's see. So, assume X is equal 0, right? So that means, that will be 0 ended with 0 complement. That means 0 ended with 1. So it's going to be 0. Then assume X is equal 1. So that means, 1 ended with 1 complement. So going to be 1 ended with 0. So going to be 0. So you are right. So X ended with the complement of itself is equal what? 0. Right? Let's try another one, which is basically what is the X ORed with its own complement will be. So we're going to do the same assumption thing. So assume, who's coming now? I don't know who's those guys. Anyway, so assume X is equal 0.
I think those guys were people like got maybe because we had 31 now it's like 30, 28. So maybe they lost connection.
Maybe. I think so. Anyway, so that means X0 ORed with 0 complement. So you're taking 0 ORed with 1. So you mean 1. Assume X is equal 1. So we're going to move to this. So going to be 1 with 0. So going to be 1. So no matter what is the value of X, this combination thing equal what? 1. So you can make our lovely golden rule, which is saying that, if I complement the variable by itself like this is equal 0, and if I OR it's going to be 1. Oh, sorry. Those are very important. We're going to use them for the rest of our classes, for optimization. So we're going to use those guys for what? Optimization. What does optimization mean? Decreasing number of gates. If I figure out a way to decrease number of gates, the circuit will be faster when I will add the response time of every single gate into the total equation. That makes sense? So if I go a little bit up here and I start looking to this weird circuit I was working with, right? Is this the only way to implement this circuit?
No.
Exactly. The other way to do it is actually to turn it back to this. Right? Which is going to be what? It's going to be the complement of X. Right? And they're going to be ANDed with the combination of the Y with the inversion of Z. So imagine this circuit will give the same thing as this circuit, but it depends on how much time it will take. You can decide. Make sense? So that's actually showing you that, with the logic, you can have infinity solution for the same problem.
Sorry, Professor, can you go up for a few seconds?
Yes.
Oh, so one of the AND gates is taken out.
Yeah, this is AND, this is an OR, this is not, and this is not.
This will be like a faster implementation for the circuit.
We don't know yet because
Or-
I'll give you another story later.
Oh, gotcha. Thank you.
Okay. Okay. Let me try something else. Okay, there is something even fun. Let me try now. We don't have that much time, but I will write something now, and then I will repeat it again next time. That makes sense? So that's actually called De Morgan. So it's called De Morgan, the theorem of De Morgan, or De Morgan's theorem. So what is De Morgan said? De Morgan came into the point that, that's actually part of what he said when he said X or X that's a part of his actually theorem. The second one, which is if you have X ORed with Y, X ORed with Y, okay? And the whole entire combination is what complemented. How are you gonna break it up? So listen to this very carefully. How can you break something like this up? So De Morgan said, if you have such a kind of combination, so the best way to do it is to start distributing the combination. Okay, so how many pieces in front of me in this combination? I have 3 pieces, right? I have 2 variables and the operator, right? Oh, the operator, I'm sorry. So that means, X complement, and then, here's the complement, and then, the Y complement, right? De Morgan simply say, if you have ending operands or operator, I'm sorry, and, your process complement on that will be inverting to what? ORing. And if you have ORing and you try to complement it, that will be what? Ending. That is called duality theorem. So, in this case, I can write this as X complement ended with what? Y complement. So very clear. If I have something like this, if I have X, Y, Z complement, how I'm gonna break it, as De Morgan said. So every single piece will be what? Complemented, right? So look, it's gonna be X complement, and then this OR it's gonna be what? And then the Y it will be complement, and then the other OR it will be what? And then the Z it will be Z complement. We're gonna practice this more next time, but I did a stick in stopping here, so at least you guys will digest the trick of the AND and OR and NOT gate with the Boolean equation and Boolean algebra. Do you guys have any questions so far?
Do we need to put the complement, or is it remove the complement to convert it to?
Distributing the complements on the entire term. So what I did in front of you, I'm just distributing.
Oh,
If somebody wrote like this, f as a function of x and y and z variables is equal to x, y, ORed, and the whole entire thing has a shared complement. So how are we gonna break it up? So in that case, it will be x, y complement, and then this OR it will be and and then you know this z, it will be z complement. Then you know you move forward, and then you know you, oh, this is still need to be broken up, right? So you're gonna break it. So it's gonna be x complement or y complement, and I'm gonna be z complement. I'm gonna do this one more time next time with more examples that will be more easy for you. So summarizing,
Thank you.
what did we learn today? We finished the gray code again, and then we also made an example about the BCD. We started with one of you asked about it, and then we went for the parity bit, odd and even, and we talked about the Ascii code, which is a basic layout we use for the keyboard as well, for different type of countries and different languages as well. And then, we will move to the gates as a basic gates and an or a not gate. We learn what is called truth tables, and we move forward to the representation in the Boolean algebra. And we learn also there is something called gate level implementations. And we moved a little bit for the theorems and the postulates related to the Boolean algebra. And we stopped in what De Morgan theorem. Any questions?
No, sir.
Okay. I hope you guys are enjoying the class, and practice. That will be the key thing. At night, a copy of this note will be under the week 3 supporting materials, and then a copy of the whole entire lecture will be under the recorded lecture folder of the week 3. Thank you, guys. It was my pleasure to talk to you. God bless you. Stay safe. See you next time.
Thank you, Professor. Awesome.
Thank you, Professor. Have a good one.
Goodbye.
Professor?
Yes, sir.
I have a question about, this is like totally off topic, but recently I have learned about ECC memory, where essentially it stores parity data for like whatever it's supposed to be. And the reason I'm kind of asking about this is because the newer AMD chips is supposed to support, like some of the motherboards are actually supposed to allow you to support ECC on just a normal like computer consumer rig instead of like using a server. Do you think that would be beneficial to put that in a consumer grade system, or should I just stick with like regular, DDR, just plain of the old non-ECC memory?
I would say go stick with a normal DDR.
Right. Is ECE kind of expensive?
It is.
Okay. Yeah. Okay. And so I wasn't too sure yet. I haven't even looked at like where to buy ECC yet.
You're fine. Okay. Thank you.
Yeah, you bet.
Any other questions, guys? Okay. See you guys.